Hello, welcome to this tutorial series on distributed systems. I am Balasubramanian. Today we are going to look into an interesting problem statement. The problem statement goes like this: how do we handle failures while we event out? And we are going to take one of the approaches which is called hinted handoff to solve this problem statement. So let us look into the problem statement and understand what the problem statement is, what are the possible solutions, and how we can use hinted handoff to solve this problem statement. Let's look into this in this order. Okay, so while we do business transaction, there will be lot of events which will occur, like payment happened, uh, credit card number valid, order placed, item added to the cart. Several such events, items out of stock. So many events will happen, and there are a lot of systems which are interested in the occurrences of these events, and they will take critical decisions with the events that's occurring or that has occurred during a particular transaction. Let's take one simple example. The first example is e-commerce. Everybody would have shopped at least once via e-commerce websites, right? So while we do shopping, we add items to the cart, and then we finally check out and then place the order. And while we place the order, we do the payment. So once the order has happened, there are a lot of systems or downstream systems should be interested to understand, okay, whether new order has arrived. One such system we can talk about is the finance system, right, which will go and reconcile the payment between what is the order, what is the payment, whether I did receive the same payment from the payment gateway or the provider as such, whether it is settled or not. That's one we can take. The other is the supply chain systems. Once the order is placed, the supply chain will go into the fulfillment part. So they are interested in the order placed events, and they will have to plan the inventory and start the shipping process during that. So this is one example in e-commerce. The other system, we can take one more example or two more examples to get a solid understanding of where are places we will event it out, right? We will take two, three different scenarios. The second statement that we can think about is fraud detection systems. For example, if somebody try to log in from one machine with a credential which whose IP is from Asia Pac, and in the next moment somebody tries to log in from an IP which is originating from Europe, it potentially means there can be a person who is trying to get into the system. So these fraud detection systems, either on payments or, for example, even take the credit card. If we are trying to make a payment from India, and in the next moment we are trying to make a payment which is originating from America, it means potentially there can be a fraud, because the source IPs which the transaction is originating might not be the pattern which the user used to originate the transactions. So these are the systems which will be listening to such events, right? So they are required and they have to receive these events on a timely basis, and it cannot fail. When it fails, it will cause problem to the entire system. The third, take a very simple example for people who have not into large scale enterprise development. This take a very small attendance system or something, right? Any person who is applying for a leave, right? They will go and say that I have leave and I will apply. But there are other downstream systems like finance systems who will have to listen to the occurrence of leave application from an employee, and they will calculate the monthly salary based on that. So those are all systems which will be listening to the occurrence of these events. These events are the systems who listen to these events need not be notified synchronously, but they can be notified asynchronously also, interprocess communication. But they need to get it in a timely manner. If they are received in out of order, if they are not received on time, then it causes a chaos in the system, or it causes business impact to the system. Let's this is the problem statement that we have to talk about today, or we are talking about today. Let's go into the text that we have come up with. Back office systems which are not involved in online transaction journey. It's one such example, need not be as well, right? Online transaction journey depend on the notifications to initiate additional workflows. The additional workflows are the workflows which we talked about. In distributed systems, of late we most of the applications that we develop uses somehow or other microservices architecture. When we go into the microservice architecture, they are loosely coupled for particular domain. For example, customer order is a domain, payment is a domain. So these domains will communicate to each other via defined contracts or defined events, right? When an event happens, we need to notify them. The nature of distributed system that any time some node may go into a temporary failure. Okay, when such failure happens, the originator of the event tries to notify to the subscriber of the event, and the eventing system goes down transiently. How do we notify them so that we don't we don't fail on our SLAs? For example, these transaction systems, can the ordering system wait for all the events to be published, then only the customer order is satisfied? No, we might not be able to, because there are a lot of people who will be listening to the order event. Starting from the notification to the customer, email and SMS notification, to the payment systems, to the supply chain systems, to the fraud detection systems. Every system will be more than tens or fifties of systems would be listening to these kind of events in a bigger e-commerce site. Okay. Maybe the scheduling system, which has to ensure that the orders go on time, right? Those all people will be waiting for these events. Can we go and make the order a success only when we notify to all 50 people synchronously? No, we would not be able to scale online transaction processing systems at heavy load, or even whatever load it is, waiting for us to notify 50 systems. But we need to notify into the particular eventing system, so somebody can subscribe. So it is a most of a publisher subscriber model we are talking about. And when we are trying to publish to a from our side to an eventing system, or to a streaming system, might be Kafka or whatever it is, there might be some cases where network partitions can come, or we might not be able to communicate to them transiently. How do we handle errors is the problem statement that we are looking for. Uh, so since I have explained the problem statement in a much elaborated way, what are the problems that we will face when we don't send this, when the downstream systems or the other systems who are interested in it? It might result in financial losses. Maybe if we are not detecting the fraudulent transaction, it would result in a financial loss to the customer, or even to the even producer, or even the service provider. Customer not receiving notifications on time would bring down the customer satisfaction, or the trust, customer trust will come down. If you have submitted an order and if you are not receiving notification that the order is accepted or not, for example, in this pandemic, people are booking for the blood test. So when we submit a request for a blood test and we are not receiving notification saying that your request for the test home pickup is accepted, and a person will be visiting on so and so time. If we are not receiving the notification, we get confused that whether we have booked in the right way, all these things. So it will result in customer dissatisfaction and the distrust of the customer to the system as well. So the criticality is very severe, or it's high impact. It makes a high impact. So eventing systems, the publisher has to notify in a consistent manner, and they have to handle these transient failures, and it is very critical for the business process. So there is a criticality around this system which we have to solve this problem, and we need to solve it in the problem so that we don't fail, and we will be capable of we don't fail is a big statement, but we handle failures in a graceful manner, so that we are good enough when we are trying to uh, handle the temporary failures or temporary glitches in the system by strictly adhering to the SLAs, because while we are doing all these things we have to adhere to the SLAs. These are the 3 points in we have to keep in our mind while we are designing such systems. After looking into the problem statement, since we have gone depth into the problem statement and we have analyzed some of the use cases where these problems can occur, and we also understood about the criticality of how events has to be handled. Let's look into how the flow goes with the help of a diagram. A client sends a request, it will be load balanced, and there are a lot of more than one machines which are trying to process it, and it has to write the data to the database. That's the primary role. But after the data has written, we got a confirmation that we have written the data. We need to publish it to the we need to publish the occurrence of the event to those people who are interested in it. So I have taken an example for as a Kafka as a streaming system, but it can be any system as such, right? If we have the eventing out, an enterprise may choose this is the eventing system. It can be Kafka, it can be Apache Pulsar, or maybe we can put it into a queue where more than one subscribers are listening to it. So this is the flow that we are talking about. But this notification happens only when or only after we are able to write it to the database. Right now I've used Cassandra as a database. Maybe you can think of writing to any SQL databases like Postgres, MySQL, or whatever it is, and it can be any streaming system. So this is the use case that we are talking about, and this eventing happens after writing the data consistently to Cassandra or somebody. So where the failure may happen, right? So we need to understand. So I have written successfully to Cassandra. If I am not able to, when the client sends the data, and we are trying to the server, the system which tries to write to the database. After it has written to the database, I am not able to communicate to the Kafka or the event system on a transient basis. Maybe Kafka is operating at load, or it has occurred a network partition, or I am not able to do it. But think of the situation that I have to respond back to the customer within 100 millisecond for every request which I am receiving. That's what we can think of, right? In that case, how do I handle this failure? This is where we can use an approach called hinted handoff. Although, so what we can say is this problem we need not go to hinted handoff if we have a sufficient SLA time. What we can do? We can use a pattern called retry pattern. What retry pattern does? It does a retry. It will try to retry, and it will try to notify the message more than one times based on the configured number of retries. For example, before you say I am not able to notify, I will retry 2 times. Hinted handoff can be used along with retry also, but hinted handoff can be used without retry also. Okay, there are two situations where hinted handoff can be plugged in. Let me come into what is hinted handoff later, but understand that we can solve this with an approach called retry. But during the transient failures, while we retry also, if the retry window is much longer, we would be able to retry it and then notify it. But not all the time retry also works. Even if the while retry for 3 times with a back of time and a jitter time, we will cover up on the retry pattern in a different video altogether, because retry pattern itself is worth of a video to be looked into. But we can use retry pattern to handle transient failures, and most of the time retry also works with its retrays alone. We should be able to come back to the normal place. But even after retry fails, or even without retrying, suppose that I don't have SLA, I have to respond. All these services has to respond within that 50 millisecond, and a single retry will even cost us more than 50 millisecond to the or 10 millisecond to the transactions, and my system is transaction bound or time bound. I would not be able to retry. So during that situation, hinted comes into the picture. So how do we handle the failure using hinted handoff? Is the solution that we are looking into. So what is hinted handoff? Since we talked enough about what is the problem statement, and we also looked into where the failures will come. What is another way of solving without hinted handoff with retry? The next step is what is hinted handoff. So what is hinted handoff is something whenever there is a failure which happens, but we know that successfully we have persisted the data into a system where the data consistency is good, and we have persisted, for example, a database, and while we are eventing out we are failing, we can store the entire event along with the metadata into a local file system which will also not fail, right, or append to a file system, so that we will be able to respond back very quickly without doing a retry, but another process will go and retry and try to push it to the subscriber, or push it to the eventing system or the event queue, or even the pub sub system at its own phase in the order of the event which is received. Let me read what it is. In hinted handoff, whenever a notification fails, the entire data of notification along with metadata when it is occurred and all these things is stored as a hint in local persistence. What am I doing? I am trying to append. I've just used a word called stored. You can replace the stored as an append word here. I am appending into a hinted handoff queue. Okay. Note the data is appended, which ensures that the order of occurrence of events is also preserved. Once the connectivity is established, or when we are able to establish connectivity to the eventing system, there will be a separate processor which will drain from the hinted handoff queue and then push it to that system. So here what are we ensuring? We ensure that we will be doing a good amount of effort to try to notify the downstream systems. That's the first point that we are doing. Here, since we are writing to a local file system, which is an append only file or append only whatever it is, right? Let's go into the data structure little later, but we are just appending to a file. Assume like what it takes to write to a log file. It takes no time because all of our production systems write to a log, and the log gets shipped to a centralized server or whatever it is, right? If we are not able to ship the log to the centralized server, it will do a retry and it will publish it. But what I am doing, I am not waiting for the log to be published to the centralized server, but I am writing to a local. This is one thing which we have been using it for very long time, and this is called hint. In terms of hint, what we are doing, the entire occurrence of the event plus the occurrence metadata is stored in the file, and with exponential backup, the hints are retried for several number of times and then pushed to the eventing system. So what is so let's look into the diagram. There are some issues with this approach also, which we need to handle it cautiously, that we can cover up in the subsequent videos. But since we have talked everything theoretically, it would be good if we can understand with a diagram. Let's look into the diagram. A client sends a request to the load balancer, and the load balancer sends it to the processor, or take this as a REST API or whatever it is, right? And it writes to the database. When I am trying to notify to a Kafka or a eventing stream, I fail. When I get a failure, I immediately append to the file system as a hinted queue. It will take extra 1 or 2 milliseconds to do it, and then respond success with this person. This is what I am talking about on this is called hinted handoff. What I am going to write, what is the occurrence of the event is what I am going to write. What am I publishing to the Kafka is the same thing which goes here. So that next time when I come and pick it up, I will go and pick it up and push it. It is the same data plus extra metadata when it failed or whatever it is, right? We can add what metadata we want, but that's how it is. So this is the first step we are doing, right? What is the second step? How am I going to process it? Let's look into that also as a diagram. A client sends a request to the load balancer similarly, and it tries to write to the it writes the database, and I am able to successfully persist it to the database. I try to notify to Kafka where I am getting a failure. I write it to the hinted handoff queue. while I write, after I have written successfully to the hinted handoff queue, there will be a hinted handoff queue processor which will drain the message. As soon as I write to the hinted handoff queue, this will be running as a sidecar in the entire application here. So as long as this application runs, this application also runs. When this fails, this will also fail. So let think this hinted queue processor as a sidecar here. This file system is a mounted file system. So for example, next time when I come up, I will be able to get the data from this mounted file system. It will not go away. This is a mounted file system. So I'm going to get the container and mount it with this. So I will write it to the persistent store. This hinted processor will come up, which is a sidecar hosted along with the main application. And when this will be listening to this hinted handoff, whenever some write happens here, this person will start trying it out while writing to the Kafka. Okay. Let's look into the flowchart or as well, how this goes, right? This is the high level architecture we have talked about. Let's look into the actual flow also with the flowchart which I have come up with. We have a hinted queue processor as a sidecar. What is a sidecar? It is a term which is used in distributed systems where when we are containerizing an application, right? The container will execute one process as a main process. Whenever the main process goes down, the container also goes down. But what if we have to have additional executables as part of it, and it does its own work, but it can only work as long as my main application is running. Let's take this example. I will give an example so that it's easy for somebody to for every one of us to understand as well, right? So we usually write to log files, okay, but the main application would be a jar or a Go exec or a Python application which would be writing to the log file. There will be usually a log agent which is installed, which will go and ship the logs to a centralized logging repository. It can be Datadog, it can be Splunk, or it can be Elastic, or whatever it is. While we append the data to a file system, the log agent will take the data and push it. How long the log agent will run? As and when till it will run till the main application is running. When the main application crashes, we need not have the log application running, right? So this the log forwarders or the application monitoring agents, those are all deployed along the within the container as a sidecar. It will not be a main application. It is a sidecar. Sidecar is something like a in old movies you can see in a bullet or some two-wheeler, there will be a small sidecar which is attached where people used to sit and come along the bike, right? It's sidecar. Sidecar runs as long as bullet runs. After that, it will not run. It cannot run on its own. It needs the main application to run. That's a strategy we are using it for processing the messages from hinted handoff queue. This is called a sidecar pattern. We can talk about sidecar later, but while I talked about how am I going to deploy it as I have used this term called sidecar. This sidecar will check for the availability of the eventing platform with retry and backup. For example, if as I said, right, in an online transaction system, if we want to retry 3 times and after that I am not able to do it, then also we can write to the hinted handoff, and this hinted handoff queue will be drained by the hinted handoff queue processor. Along with the retry also hinted handoff can exist. Without retry also hinted handoff can exist. Both places hinted handoff can exist. So this is going to add a little more. We are going to give it a last try to notify to the downstream system. So that's something which we are going to do. Once the transient failure is handled, this will get drained. While we are storing the metadata, we would be able to publish the event with the occurrence date and time. So the consumer of that, the subscriber also will know that the occurrence of the event, and they would be able to handle it. So that's why you might see that sometimes when we do online transaction, the money transaction, so this is processed, right? We may get a little delayed notification. Those are all the times where we might have faced the transient failures. Maybe the application is operating at load or whatever it is, right? If Kafka is operating at a load, we get an error that too many requests at this point of time. During that time, we can write to a hinted handoff also. For example, when we are doing an online, when we are doing a request, wherein which we have to call a dependent service, and the dependent service is operating at full load. But we cannot, but we need to try it again. So we can write it to the hinted handoff and send the response back to the customer later also. These are all the places where hinted handoff is used. So where do I get knowledge about hinted handoff? Is it something which Balasubramanian has come up with an approach? No. Hinted handoff is an approach which is used in Cassandra, in InfluxDB, for write consistency, right? So just go and refer to hinted handoff here and read about that article in Cassandra, InfluxDB, and all. So we would be able to understand that how Cassandra and InfluxDB uses hinted handoff approach to persist the data into their system in a consistent manner. So similar approach can be used in these business transactions while we are developing distributed systems. That is the approach that we have taken, and there are many samples we have looked into it. I think we have came almost to the end of the session, but while we look into the flow chart, and after that we will also consider what are those things which we need to consider while we do hinted handoff, and those things can be addressed in the part 2 of this lecture. The application starts, and this is the online transaction processing system which writes to the DB, and the same online transaction processing system writes to the eventing. But if it tries to write to the eventing, there is a failure happens, it goes to the hinted handoff, and a sidecar which processes it will try to publish it to the eventing system at a later point of time. This is the flow. If you want to understand this. So what are the problems which we need to solve, and how can we solve those problems? This approach does not come with all without any risk, right? There are risks. What are the risks? What if the hinted queue becomes so large? How do I handle it? Those are all things which we will look into next time. Till that time, thanks for your time, and do subscribe to my channel. Bye.